Here's the exam 3 key. We're asked to name both of these compounds. This is a simple ketone, and we can number it starting at the side nearest the carbonyl. So it becomes hexane, which becomes hexanone, and has a 2-methyl. And 3-hexanone. If you want to write 2-methyl hex 3-one, that's fine too. I prefer putting the 3 in front. This is an ester with an R group right here. The isopropyl is the R group. So we would write the R group first. And then we'd put a space, and we'd name the carboxylic acid portion as a carboxylate. So we have 1, 2, 3, 4 carbons. That's butanoate, isopropyl butanoate. So butanoic acid is the 4-carbon carboxylic acid. It becomes butanoate when it's in the ester form. Question number 2 asks us to circle the reaction that we think will work the best. So let's look at these reactions. It looks like we have a slightly different mix of starting materials. The goal is the same product. So we're going to either, we're going to acylate this alcohol somehow. We can do a Fischer esterification with acid catalyst, losing water in the top reaction, or we can acylate this alcohol using an acid chloride and pyridine to soak up the HCl in the bottom reaction. So which of these would work better? Really, they'll both make an ester. I think the thinking comes down to the fact that we have a chirality center and we have an alkene here, and we want them to be maintained throughout the reaction. We don't want the chirality center to be racemized or inverted. We don't want the alkene to react with anything. And if we add a drop of acid, we could potentially protonate the alkene, maybe add water because we're producing water, or we might protonate the OH, lose water, making a secondary cation, adding water back. That would give us a racemic mixture. So that might scramble the stereochemistry right here. So that tells me that the bottom one is probably better. And so let's write up here, HCl could racemize the stereocenter or react with alkene. On to part B. Again, the products are the same. It looks like we are producing a ketone. We can either start with a cyanide, a nitrile group, and then produce this portion of the ketone, or we can start with an ester, and looks like we're going to add a 2-carbon chain to get to this ketone. So which of these works better? Well, if we remember that Grignards add to esters, they add twice though. So I think that rules out the top one. Even if we don't add 2 equivalents of Grignard, they still add twice and leave some starting material behind. That's because the ketone is more reactive than the ester. So as soon as one Grignard reacts with one ester to make one ketone, we now have a ketone much more reactive than all the rest of the starting material esters. So the next Grignard probably is going to react with the ketone, giving us the double addition. And especially if we didn't add 2 equivalents of Grignard, we'll end up with 50% ketone, 50% starting material. 50% double addition, which would be a tertiary alcohol, and 50% starting material. As we learned in class, the nitrile will accept 1 Grignard to make basically the imine, or the imine anion. We can protonate that and hydrolyze it to make the ketone, so the bottom reaction works great in this case. The third one looks like we're setting up a crossed aldol addition here with NaOH. We're going to make this bond right here. We want to attack the aldehyde and use one of these carbons on acetone as the nucleophile. The second choice, or the other choice, makes the same product, but we start with acetone, then we deprotonate irreversibly with LDA, then we attack the aldehyde, and then we'd work it up with mild acid. So the question here is, the top reaction is a crossed aldol. And if we mix all these species together, that's what this implies. Ketone, aldehyde, and base are all mixed together. We could deprotonate here some, using that as the nucleophile, and that's undesired. We might attack the ketone with either the nucleophilic ketone or the nucleophilic aldehyde to get another possible product. So we're going to get several other products besides just this one. In this case, though, we deprotonate 100% of our acetone, then we'd react that as the nucleophile with the aldehyde as the electrophile 100% of the time, and then we work that up with acid and we end up with our desired product. So the bottom one is definitely the best choice here. And we'll say that the top one is a crossed aldol. We'll get multiple products. On to the next page. So here we're asked to rank these molecules according to acidity. And so if obviously this is the acidic hydrogen on all of them, that is the same. The difference is the R group on the para position of the ring. And we know that the more electron withdrawing that group is, the better stabilization the O- of the conjugate base will have. So we want to look for the most electron withdrawing group. And we can think back to the electrophilic aromatic substitution chapter, where which one of these is the strongest deactivator? Which one's the strongest electron withdrawing group? It's going to be the ketone. So that is the most acidic. And the least acidic would be the weakest deactivator, or the activator. This one donates electrons to the ring, which would push electrons towards the carboxylate, which already has a lot of electrons as a negative charge. And so that is a destabilizing effect. So we would number them like that. Number 4, we're asked to predict products or fill in reagents in the box. I would like to point out that over the past couple years, we've slowly built up these types of questions with perhaps 2 or 3 steps. These questions are all one step, but don't be surprised if you see 2, maybe 3 steps over the arrow on an exam in this class. First one, diisobutyl aluminum hydride. That's going to reduce esters to form aldehydes. It does not reduce the aldehyde, it just removes the OR group and installs an H there. Part B is a aldol reaction. In fact, we did this in lab, more or less, with vanillin. We've got a aldehyde that has no alpha hydrogens, so there's no competition. We've got acetone that can attack the aldehyde, and it will produce, because there's heat, it will produce the alkene. C is taking the carbonyl carbon and putting 2 ethanols on it to make an acetal. This is simply alcohol and catalytic acid. If you want to put 2 equivalents of alcohol, that's fine, but it's pretty much understood whenever we have alcohol. This reaction is taking the acid chloride and turning it into an amide. Here, it is essential that we use 2 equivalents of the amine, and one of them is going to be a sacrificial base to soak up the HCl that's produced when we have our reaction. So this is just a acylation of an amine reaction, a carboxylic acid derivative. Part E, we have strong acid and water. We're going to hydrolyze the nitrile, and that's going to hydrolyze all the way to the carboxylic acid. There's no way to stop it at the amide step. So we're going to hydrolyze this all the way to the carboxylic acid. Part F, this is an imine formed from hydrazine, and this is the Wolff-Kishner decarbonylation reaction. We're going to lose the carbonyl. This started from this carbonyl and H2NH2. That made the imine we see here. KOH, water, and heat basically removes all of the functional groups and leaves us with, in this case, the unfunctionalized alkane. Part G, we have an amide. We've got SOCl2. This is going to dehydrate the amide, removing the O, removing the H, both H's, and forming a triple bond between the C and the N. So we're removing water from the amide, forming a triple bond between the C and the N. And H, lastly, is a simple imine formation. We've got acid and amine. Probably better to write H2SO4 in brackets here, so I'm going to fix that for you. But that's simply imine formation with water as a byproduct. Question 5. Write a reasonable arrow-pushing mechanism for the following fun with acid amide hydrolysis reaction, and I want you to pretend that we didn't provide you with the answer. That is probably what you'll see on upcoming mechanisms in quizzes and exams. So predict the product and draw a good mechanism. So basically we have acid present and we have water. Again, H2SO4 catalytic plus water. It's really the same thing as H3O plus, so I'm just going to use that. So the first thing we do whenever we have a fun with acid problem is to protonate. Now I have a better electrophile, and water can add to that electrophile to make this species. And I need to remove a hydrogen from this so I can put it somewhere else. And I'm going to do a proton transfer. I sort of regenerated H3O plus, and of course I could protonate this OH, or I could protonate the NH2, and I hope you'll agree with me. If I protonate this OH, I'm just going backwards, so it's really not productive. That doesn't mean it doesn't happen. In fact, it may happen more than protonation of the N. It's just that it's not productive in our reaction mechanism here. So now I basically have an ammonia hanging off here, and I can eliminate that pretty easily by this loss of leaving group reaction. And that leaves me with basically a protonated carboxylic acid plus ammonia. Ammonia is the best base now, so I'm going to use that to remove this last hydrogen. And that's going to take me to the product. And I'll redraw the product for you. That takes me to the non-protonated carboxylic acid. And it takes me to NH4 plus. If you just drew NH3 here or even forgot about the NH4, I don't really care. This is really what we're looking for. So this is the amide hydrolysis using catalytic acid and water. The next question is also an arrow pushing mechanism, and I'm going to say, again, pretend that we didn't tell you what the product was. So let's predict the product along with the mechanism. So we have water, acid, and Br2. When we're in acid, the carbonyl can get protonated, of course. And we can set up an equilibrium, or an enol, I guess I should say, formation. And we can do that simply by, sorry, that's not an H3O plus there. We can do that by removing the alpha hydrogen and pushing the electrons onto the O, and that gives us the enol. And this is going to be in equilibrium with the ketone. Maybe there's 1% enol, 99% ketone, but in acid we have this equilibrium. And now we can use the enol as a nucleophilic alpha carbon species. We can take that alpha carbon, we can react it with bromine molecule. And of course, bromine has a good leaving group attached to it, another bromine, so we can do this reaction pretty straightforwardly. We've made bromide, we made an alpha bromo, and now I have a protonated ketone. I can put that one step away from my product. I'm just going to bring in some water. You might be asking why I didn't use bromide. Well, water's a better base than bromide. Bromide would make HBr, a very strong acid. So I'm just going to let the bromide sit around and be bromide. I'm going to let the water, which is a weak base, but a better base than bromide, grab this extra hydrogen. So this is simply just alpha bromination or alpha halogenation, as I stated in the question text. Question 7. You're given some data and you're asked to essentially decipher the structure of A and B. You can figure out A and B from maybe the reaction and the formula and the byproducts. You could figure them out from the proton NMR data here. Sometimes you'll get carbon or IR. But there's a number of ways to solve this problem. The first thing we want to do is calculate the HDI for both A and B. So for A, 5 times 2 plus 2 minus 10 all over 2 is, I believe, 12 minus 10 is 2. 2 over 2 is 1. And over here, 9 times 2 plus 2 minus 20 all over 2. 9 times 2 is 18 plus 2 is 20 minus 20. 0 over 2 is 0. So we've gone from 1 HDI unit to 0. We've also added excess ethanol to the molecule, and the difference in carbon count here is 4. The difference in hydrogen count is 10. So it kind of looks like we're adding 2 ethyl groups, which are 4 carbons. And let's see what the proton NMR shows us. The second question then is to propose partial structures that correspond to the indicated chemical shifts. So a 9 hydrogen singlet at 1.08 ppm, that is most likely a T-butyl group. And because these methyls are not 0.9 ppm, they're slightly shifted, a slight bit more than 0.9. X is probably some electron withdrawing group. We did have one HDI signal, our unit. We do have an oxygen in place, so maybe there's a carbonyl present. That might be a good candidate for X in compound A. Let's look at compound B. We are given a 4-hydrogen quartet and a 6-hydrogen triplet. And so the quartet is at 3.51, the triplet's at 1.21, and of course we can't have a CH4 or a CH6 functional group in our molecule. So maybe this is actually 2H quartets, and this is 2 3-hydrogen triplets. So that means I have some symmetry, and I have some equivalent groups here. And a 2-hydrogen quartet means I have a CH2 that's next to a CH3. The CH3 is probably indicated by this triplet at 1.21. And because the 4H quartet is at 3.51, most likely it's attached to an oxygen. I do have 2 oxygens here, so I think we have 2 ethoxy groups. I don't know what these oxygens are attached to, but I think they are there. Lastly, we're asked to propose structures for A and B that match the given formulas, the conditions, and the proton NMR data. Let me draw compound A. I think, as we said, there's probably a carbonyl. And if I have the carbonyl attached to the T-butyl group, what does that leave me in the formula? I have 1, 2, 3, 4, 5 carbons. I have 5 carbons. I've got 3, 6, 9 hydrogens. I need 10 of them, and I already have the O. So the only thing that's left is a hydrogen. The only place to attach it is to the carbonyl carbon. Does that make sense? Well, I do have this 1 hydrogen signal at 9.5 ppm. It's a singlet. It is shifted quite far, and that's what we'd expect for an aldehydic hydrogen. So I believe this is what I have for compound A. So I could fill that in up here. And now I could probably just solve for B now that I know what the starting material is. I know that it's going to react with excess ethanol. I do know that I have 2 ethoxy groups here. So I hope that you're starting to conclude that B is simply the ethyl diethyl acetal of this starting material A. Does this structure match the formula? I have 4 carbons, 5 carbons, 6, 7, 8, 9. I do have 9 here. I've got 9 H's, 10 H's, 5 more. 5 more is 20, and I have 2 oxygens. I have a 9 hydrogen signal at 1.03 ppm. That seems reasonable. I've got a 1 hydrogen singlet at 4.47 ppm. This is an H attached to a carbon that's attached to 2 O's, so that seems reasonable. And then again, these signals here are symmetrical ethyl groups, and they are certainly reasonable given the NMR data. So I believe this is B and this is A. And you can see how we can solve this using a number of different techniques. Okay, we're asked to propose a synthesis of one of these two. Might as well do both of them for practice. Let's look at the first one. It looks like if I'm going to number carbons, I would number them this way. And I would see that carbon number 3 with the T-butyl group is missing. The ring is still there. It's attached to carbon 1. Carbon 2 still has a functional group attached to it. It's now a carboxylic acid chloride instead of an alcohol. But carbon 3 is missing. So somehow we broke the bond between 2 and 3 and ended up with a carboxylic acid derivative. Now, there's one unique reaction that we learned about that can do this for us. A carboxylic acid derivative can be derived from carboxylic acids, esters, amides, acid chlorides, so forth. So this is basically the same as having a carboxylic acid or an ester or an amide here. And we can cleave bonds next to carbonyls if we have an ester. So let's oxidize this to the ketone. We can make esters from ketones using MCPBA. This is the Baeyer-Villiger reaction. And remember that tertiary carbons, which is what we have here, are more likely to migrate than primary carbons. So we will most likely cleave this bond and put an oxygen group there, or an oxygen. And we get this species. Now we have an ester, and I can turn that into an acid chloride by hydrolyzing it. This is saponification. You could probably use acid and water if you wanted to. I could make the carboxylic acid, and then I can make the acid chloride with SOCl2, and that's it. So we saw the Baeyer-Villiger reaction, which we used to create a carboxylic acid derivative, and then we used carboxylic acid derivative chemistry twice to get to the acid chloride. Let's look at the next molecule. I'm going to number some carbons here. I'm not going to bother with the methyls, but if I number, you see that I need to make a bond between carbons 2 and 3, and I need to add 1, 2, 3, 4, 5 carbons to my molecule. So the question becomes, how can I do that? I think one clue is between carbons 4 and 5. We have an alpha-beta unsaturated carbonyl species, and we know that we could make that with an aldol condensation. So maybe we add carbons 5, 6, 7 to the 1, 2, 3, 4 carbons via an aldol condensation. And that could be our final step. And really we just need NaOH and heat reacting with the appropriate carbonyl species. And now that I look at this, I see that there are actually a couple of alpha carbons here. It's possible we might get some deprotonation here, turning that into a good nucleophile. So maybe we need to rethink this. Let's use LDA and get a selective reaction going. So the first thing I'm going to do is LDA minus 78. I'm going to react that with acetone, and then I'm going to deprotonate the acetone. In the second step, I'm going to add my aldehyde, and then with some heat, we can get it to eliminate to form the alpha-beta unsaturated carbonyl species. So really acetone is easy to buy. I think it's this piece that we have to make, right? Because we have the T-butyl group here, we've got this T-butyl group. And again, if I go back to my numbering, I have 1, 2, 3, 4. So I've added a couple carbons now. I still need to figure out how to add some others. So in this case, we can recognize that, again, we still need a bond to be created between carbons 2 and 3. And I need to have a 2-carbon group added, and I need a functional group on the outside of that 2-carbon group, on the end of the 2-carbon group. We learned way back in the ether epoxide chapter that an epoxide can be used to add 2 carbons and install an alcohol on the outer carbon. So here we can certainly envision oxidizing that alcohol with PCC, and I can make this into a Grignard, and that Grignard can react with a simple epoxide, mild acid workup, to get to my desired primary alcohol that can be oxidized to the aldehyde, that can react with acetone in this aldol condensation reaction. So I've added two sets of carbons, first with the epoxide, and second with acetone to get my 2-carbon chain up to 7 carbons in this case. Let's take a look at the bonus. Here we're asked to propose a reasonable arrow pushing mechanism for the following transformation. I believe this is called a Vilsmeier salt. So how do we do this? We're going to make CO, we're going to make CO2. We've got the 2 chlorides here. We make an N cation, so we make an ammonium cation. That's obviously this N, and this carbon is probably still here. It still has the H attached to it, except that I've lost the oxygen, and I've installed a chlorine here. So let's, how can this react? Well, this is a good electrophile, oxalochloride, and an amide is decently nucleophilic at the carbonyl carbon because of this resonance. So let's take advantage of that and attack oxalochloride. And I can certainly lose chloride this way. I know that one of the byproducts is a chloride, so that takes care of that. And then I could take that chloride, attack the carbon to nitrogen double bond. So I know I need to install a chlorine on that carbon. And that gives me a neutral species. I can also push off this leaving group. That's not a bad leaving group, and I believe that will get me right to my salt. All right, so that will put a CN double bond back. It will create the N plus. It will leave me with a chlorine and an H attached to this carbon right here. And so the question then becomes, how do I get CO and CO2? Well, let's look at the leaving group. Here's my leaving group, and that's actually pretty stable. It has resonance, but we could envision it falling apart to form CO2, CO, and chloride. Given that these two are gases, that makes this process pretty favorable. And chloride is a good leaving group and pretty stable on its own. So this decomposition here is quite straightforward, quite favorable. We're going to form the gases, the chloride. That's where we get these gases here. There's my chloride, and we formed this salt during this arrow push.